So good afternoon, everybody. I stand between you and some drinks at the expo. So I did this presentation at IDUG EMEA last year, and I got some comments on the evaluation forms that it was too basic. Well, it's a beginner's session, all right? I'm happy to take comments that it was too complex, and that might actually be the case, but it is meant to be a beginner's session. Originally, it was intended for application developers, and I thought, how hard can a 1 hour session on locking be? And then I found out that it's actually a 2 hour session. So there's quite a lot of material here. So if I'm skipping over some slides, it's so that I make sure I get to the stuff at the end. But please, if there's any questions afterwards, or if there's some material I don't cover during the session you want me to cover, then please mention it. So what I'm going to talk about is some locking essentials in DB2 for ZOS. Then I'm going to talk about what these mysterious things called latches, claims, and drains are. A very small section on data sharing, and the reason it's small is because locking in a data sharing environment is a more advanced topic. So I want to cover the basics, and most of what I'm going to talk about is going to be single member DB2s. Things get more complicated when you move to data sharing. And then at the end, and as we go through, we'll talk about some hints and tips to reduce locking problems. A lot of the locking problems can be avoided by good programming practice. So that's what we're going to talk about. So, an introduction. Locking is there to ensure data integrity. It's a key requirement for ACID transactions, which is one of the concepts that's familiar to relational databases. So the idea is that a unit of recovery should be atomic, so either everything in the unit of recovery happens or nothing. It should be consistent, but only consistent after commit time. So the database in the middle of a transaction may not be consistent, but at the end it will be. Isolation. So if you've got two units of work, they can't be dependent on each other as far as recovery is concerned. Otherwise you've actually got one unit of work, not two. And they should be durable. So once you've done a commit, that database is persistent. All right? Now the reason I mention this is because some of these new databases, like some of the NoSQL databases out there, don't conform to ACID. There are databases out there that once you've got a commit, they may not be always there. But DB2 is used for transaction database management systems, and all the applications have to be ACID. Now, the good news is that DB2 always ensures data integrity is maintained. So what you do, by and large, shouldn't be able to corrupt a DB2 system. Okay? But you can control the impact of that work to do data integrity on other people. So if you want to, you can write an application that will bring your system to a standstill by coding incorrectly and taking the incorrect locks. Equally, you can code your applications in such a way that your transaction will sit nicely with everybody else on the workload. And that's what we're going to be talking about. So although, from an application programmer's perspective, you don't have to understand every option, it's important to understand the concepts and the impact they might have. So life is a compromise. And the data on this slide is a generalization, all right? But every lock in DB2 costs around the same. And as again, I'm talking about a non-data sharing system here, all right? It's roughly the same number of instructions. There may be small differences, but in the ballpark, you're roughly in the same area. And it's between 500 and 600 bytes of memory, okay, for every lock you take. Right. Now, the last time I could find a reference to that number in a manual was on the DB2 10 manuals, and I think it was about 560 bytes then. But it's in that order of magnitude. So if your only focus was on performance, you'd lock the object at the beginning of your transaction, do your work, and then release the lock at the end. One lock, all right? But then nobody else would be able to do anything because you'd be locking all the objects. So what you want to do in general is hold the smallest number of smallest locks you can for the shortest time. And that will allow everybody else to process as much as possible. And that's where good programming practice and design can help. And there's some hints and tips at the end of this session to talk about that. So where does DB2 store locks? Well, it's in a started task, one of the started tasks that runs in DB2 called the IRLM, or the Internal Resource Lock Manager. And by and large, the name is going to be your subsystem name with IRLM at the end of it. Okay? Now, the heritage of this comes from IMS. If anybody's used to using IMS, you'll see IRLMs in IMS systems as well. In a data sharing environment, DB2 stores entries in the coupling facility as well. So each member has its own IRLM, but there's a lock structure in the coupling facility that contains the locks for a data sharing system, and there's a couple of slides later on to talk about that. Now, since DB2 version 8, which is a long time ago now, DB2 has stored locks in 64-bit memory. So memory is not such an issue for locks as it used to be back in the DB2 version 7 days. So the theoretical limit for a single DB2 subsystem is around 100 million locks. But if you tried to run a DB2 subsystem with 100 million locks, I don't suspect you'd get very far. All right? So that's when you start using data sharing and some of the other things that are going on. A typical IRLM will hold around 3 million locks if you've got about 2 gigabytes of storage allocated to it, in baud terms. Right. So the full impact of where DB2 stores its locks, especially in a data sharing system, are outside the scope of this presentation. But on the last slide of the presentation, there's a bibliography, which has got some really good material where to get more information if you want it. So what I'm going to start talking about now is 4 essential locking concepts: scope, mode, duration, and isolation. All right. And we'll cover each of these in turn, and then towards the end of the session, we'll cover some more advanced topics. So the first thing is the scope. The scope is how much data are you locking when you take a lock. All right. So there are the scope is determined in your DDL, in your create or alter tablespace DDL, by a parameter called lock size, but it can also be changed by a lock table SQL statement in your program. So you could say, I want to create this tablespace with a lock size of row, and then in your program say, I want to lock the whole table. Okay? Now, lock table is a statement that you probably shouldn't be using in a general case when writing programs because of the impact it has on everybody else. Right? So the main options for lock size are tablespace, partition, table, and then either row or page. And the reason that I've got row or page is they're mutually exclusive. An object can either be using row level locking or page level locking and not both. All right? Now most applications, most systems are using row or page level locking. The default is page level locking most of the time. Right? Now, DB2 also has a couple of extra types of locks for XML and LOBs for those particular data types, and I've got a slide on each later on. Okay? Now, if you look at the syntax diagram for DB2, you'll see there's a lock size any clause, but there is no such thing as an any type lock. So if you say lock size any, you're allowing DB2 to decide the lock size. Now, most of the time, it's going to choose page level locks. But one thing I found when I was doing the research for this presentation, which is not generally known, is if you code implicit table spaces, you're using row level locking by default. So those DBAs who are coding tables without creating table spaces because they're too lazy are implementing row level locking without even realizing they're doing it. And in a data sharing system, that could cause some impacts. All right? So that's something which I've only found out when I was doing the research for this presentation. So this is the hierarchy. DB2 has a locking hierarchy. For simple and segmented table spaces, you've got the table space lock and then either a row or a page lock. And if you've got segmented table spaces that are multi-tables, you can actually lock the individual tables within those as well. For a partitioned object or a UTS of any type, whether it's partition by range or partition by growth, you've got a partition lock and then a row or a page lock. Note there's no tablespace lock for a partitioned object. DB2 is only locking it at the partition level. And then there's a couple of XML and lobs, which we'll talk about later. So if you say that I've got a row lock or a page lock for your object, DB2 can escalate these locks to a higher level. And that's managed by this parameter called lockmax. So when you create your table space, you say what lock type you want, and you say how many locks you're allowing to be on that object before that lock type is being escalated up to a higher level. Now the default is in a zparm parameter called numlockTS, and in DB211 the default is 2000. All right? So a table space can have 2000 locks on it by default before the locks start getting escalated up to a higher level. And as you can go back to this, if you start locking a partition rather than a row, you can imagine you're locking out a lot of people. Question?
I thought that locks escalation is at the thread level, so not total number of locks, but as a thread accumulates that much, then it is escalating.
Right. There's another parameter which I'll talk about in a second. So if you will let me go on to the next slide, I'll cover that then. Okay. But it's a good question. So now what's another thing to be aware of is that if you say lock size page or lock size row, DB2 doesn't default to this parameter. It defaults to lockmax 0, which means no escalation. So if you specifically say lock size row and you don't specify a lockmax parameter, you're getting no escalation. All right? Now that may or may not be a good thing because there's a cost involved in locking. So escalation goes up the chain. So if you're at row or page level locks, it goes up to partition. Over here it goes up to a table and then up to a table space and so on. So as you can imagine, it's critical to avoid lock escalation. All right? Lock escalation is a surefire way of destroying a subsystem. And your system programmers or your DBAs will be monitoring your DB2 system to make sure that you don't get lock escalation. All right? And the way to avoid it is to make sure you commit frequently. And by sure, you need to make sure that you commit before you reach this number. Okay. Now the question we had earlier about the number of locks for an individual user, that's the numlock_US parameter for a number of locks a user can hold. And that's the number of locks a user can hold across the object, across all objects. And by default in DB211, it's 10,000. All right? Okay. Now, this is only for page or row level locks. It's not for the higher scope locks, the table space or the table locks. And if you exceed this numlock_US number, then your application is going to abort with a -904 with this reason code, 00C90096. Okay? So we've talked about scope. Let's go on to modes. So a mode is what type of lock are you holding? So is it, when DB2 started in version 1.1, there were only two modes. There was shared and exclusive. There was no update lock at all. And update locks were added in DB2 1.2. All right, but that's in about 1986, so it's a long time ago. All right. So you can see the lock table here. Share locks are compatible with each other. Share and update locks are compatible, but you can't hold a share lock and an exclusive lock. Makes sense? And the reason that U locks were added was to make sure that two applications didn't get deadlocks. It reduces the number of deadlocks, but it only reduces the number of deadlocks provided you code fetch for update of. If your select statement has fetch for update in it, then you're basically telling DB2 that you're intending to update that row, and DB2 is going to take a U lock, not an S lock. Right. And then when you actually update the row, the U lock is escalated to an X. Right. So if you look at it, two ulocks are not compatible with each other. So if two people try and update the same page, then the second one's going to wait. Okay? Now, these locks are for page and row locks, which are the ones at the bottom of the hierarchy. For the higher hierarchy objects, DB2 also looks at SU and X locks, but there is another type of lock that's held at this level. So if you imagine a scenario when you have an object and you're using page level locking, and you've got a share lock or an X lock on that page, and you issue a lock table statement that's incompatible with that. Right. So say you've got a share lock on the page, and you say, I want to lock the complete table space exclusive. But somebody else has got a share lock on the page. All right? So now, DB2, if DB2 didn't have these other type of locks, DB2 would have to look at every page of the object to determine whether there was a compatible lock on it before it could take the lock escalation or the lock table statement. So what DB2 does is it takes these things called intent locks. And if I go back to my diagram, so if you've got an X lock at the row level, then DB2 is going to take an IX lock higher up the hierarchy. So now when you issue this lock table statement, DB2 can see that somebody has an X lock lower down because there's an intent lock higher up. So it only has to check one lock, so it's much better for performance. Is everybody clear on that? I didn't explain it very well, sorry. Okay. So you've got intent share and intent exclusive to handle these two. And you've got these mysterious things called 6 locks. Share with intent exclusive. All right? I've been working in DB2 for 28 years now, and I've never seen one. Okay? So how do you get one? Well, what you do is you take an IX lock and then issue a lock table for share. So you've got a page or a row lock locked out at the exclusive level. Going back to my diagram here, I have an exclusive lock at the row or page level, which means I have an IX or an IS lock here. And now I take a lock table statement, a lock table with share mode. So DB2 has to lock the table in share mode with an IX here, and you end up with an SIX lock. So intentionally, you can almost ignore them. They're very, very unusual beasts. So this is the lock compatibility matrix for these higher scope locks. And you can see it's very similar in the middle here with the S and the U and the X, but then you've got the intent locks here as well. And generally, an intent lock is compatible with another intent lock, but intent locks aren't compatible with things like X locks. Okay. So lock contention and timeout. If DB2 encounters an incompatible lock, it will sit and wait for that lock to be released. By whoever's got the lock's going to have to do a commit. Okay. And DB2 waits for a defined time called the IRLM wait time, which is another ZPalm. And the default is 30 seconds. All right. So DB2 could sit and wait for up to 30 seconds, or for at least 30 seconds before your application will sit and wait for at least 30 seconds before it times out. All right. Now we all know online transactions, 30 seconds is a long time. All right. Now in practice, the actual time you wait is slightly longer because there's a thing in DB2 called the Deadlock Detection cycle, and that runs every so often. So what DB2, and if you look at the notes of this presentation that are on the slides that you can share, you'll see the actual time, but it's the IRLM wait plus the deadlock detection time, basically, is the maximum time you could wait. So it's at least 30 seconds and up to 31 in a non-data sharing system, and there's a formula for the data sharing system one on the notes. So if you get a lock timeout, you'll get either a 911 or a 913 with a 00C9008E reason code. Deadlocks. Most lock contention is handled by waiting. So DB2 comes across a lock and it sits and waits. Okay? Deadlocks are different, and they're not always avoidable, but the vast majority of application deadlocks are avoidable by good coding practice. So what is a deadlock? Well, what we've got is application A comes in and it places a U-lock on page A. Yeah? Application B comes in and takes a U-lock on page B. Okay? Now application A comes in and tries to exclusive lock this page, the one that application B has already got. If that's all it was, everything is good. All right? When application B commits, that lock is released and the first application carries on quite happily. But now what happens is application B goes in and tries to take an exclusive lock on page A that application A has locked. And now neither application can continue. Application A is waiting for application B is waiting for application A. All right? Sometimes called a deadly embrace. All right? It's called a deadlock, and DB2 looks for it on a regular basis. If it spots this, it's going to abort one of these two applications. Okay? So I already mentioned earlier, DB2 has a thing called a deadlock detection cycle. It defaults to every second. On one application of those two is selected by DB2 to abort. And you can't tell it which one. DB2 chooses which application to abort. Now there is one exception to that. If you've got a not logged object, a DB2 not logged object, which aren't used very often in OLTP systems, DB2 will abort the other transaction so that it doesn't end up with a recovery situation. All right? But by and large, you can't control which SQL statement, which application gets aborted. So how do you avoid deadlocks? The key, from an application perspective, is to process tables in the same order, objects in the same order, and preferably rows within the object in the same order. So if you go a customer number before the order numbers, and then do it in customer order, for example. So if you code an application so it accesses the data in the same hierarchy, in the same order, then you massively reduce the chances of getting a deadlock. Okay? Now you can't avoid them completely, because DB2 may end up with bits of rows on multiple pages, and you may end up with problems that way. You can't avoid them completely, but you can avoid the vast majority of them by good coding practice. So let's cover duration. So we've covered scope and mode. So next thing is how long the lock is being held for. Now there are two bind parameters. There's a bind parameter called acquire, and there's a bind parameter called release, and there's your commit in your SQL. And between them, those things control how long locks are being held for. All right? Now, the bind option acquire has been redundant since DB2 version 10. All right? So you used to say acquire use or acquire allocate, and DB2 always uses require use now. Even if you code acquire allocate in your bind, DB2 is going to use acquire use. So we can effectively ignore that one. All right. The release options are either commit or deallocate. And bear in mind that these are for page and row level locks only. So these are the bottom of the hierarchy. So if you code commit, it's the other way around. Page and row level locks are always released at commit time. These bind parameters are only account for the higher level locks. Sorry about that. So if you code release commit, the tablespace, the table, and the partition locks are released when you do a commit. The only exception being is if you've got a cursor with hold and DB2 needs to maintain one of the locks to maintain cursor position. All right. But by and large, the tablespace, table, and partition locks are released at commit time. All right. Now, if you have got a cursor with hold on, and you've done something like a lock escalation, so if you started with page or row locks and you've escalated to a tablespace lock, DB2 might still downgrade the locks back to a page or row level lock, so you won't have an escalation situation anymore, but it will still maintain the lock. The other option is deallocate, and release deallocate releases the locks when the thread terminates, so when your program ends. All right. Now that releases locks, it's lower in resources, because if your program is doing multiple commits, DB2 doesn't have to continually allocate and deallocate the locks. All right? So it's lower end resources, but obviously it holds the locks for longer, and it can cause application issues. All right? So in DB2.11, IBM introduced a change to release deallocate. So most people were using release commit up until then. But release deallocate is much better for performance. So it saves you releasing and reacquiring locks. And if you're using distributed DB2, there's a thing called a high performance DBAT, which is much faster. And you need to have release deallocate to get a high performance DBAT. All right. Now the trouble with release deallocate is if you've got a long running unit of recovery and somebody initiates a reorg, then the reorg can't break in or couldn't break into the application to do the switch phase at the end of the reorg. And the same thing happened with DDL. If somebody wanted to do DDL, then the DDL couldn't complete because you had a lock on the object. So there's a new ZPARM called package release commit in DB2.11. And if you've got release deallocate coded in your bind parameters and you do a commit, DB2 checks to see if there are any package locks outstanding on the objects. And if there are, it converts the package temporarily to release commit. That frees up the locks and allows the reorg or the DDL to break in, or the command. And then once those have completed, it goes back to release deallocate again. So effectively, you're running release deallocate. It switches down to release commit and then back into allocate again. And it allows commands, DDLs, and utilities to break in. All right. So it's a really nice feature of DB2.11. Now this is a beginner's session. That's not a beginner's topic. If you think that might be something you're interested in, go and talk to your DBA and see if you can benefit. All right. Because you're not going to be, unless you're a DBA or a systems DBA, you're not going to be allowed to change DSN ZPARMs. And the last of the four major features is isolation. Now, isolation covers two aspects. It's what do you do if you come across a lock held by somebody else? And it's what are other people allowed to do if they come across a lock held by you? So effectively, it gives DB2 a behavior for what happens if you come across a lock. Now, the good news, as I said earlier, there's no application integrity exposure because DB2 always maintains application integrity whatever happens. All right. This isolation is handled by a bind parameter called isolation. So when you bind your plan or your package, there's an isolation parameter. All right. I'll explain what the isolation parameters are. Afterwards, I've got a couple of slides on how to override it. Now those overrides are more advanced topics, but I'm putting them in there for completion purposes. So these are the first two isolation options. Repeatable read. When I started working on DB2, spoofy was bound with repeatable read. So everybody used to go into spoofy and sit there and they'd lock the application out. All right. So what a lot of people used to do was they used to change the spoofy plan to use cursor stability. All right. I don't think you have to do that anymore. I think IBM do it by default. All right. Now, with repeatable read, if you read a lock, if you try and read something and it's locked, you're going to sit and wait. All right? So all the data you read is going to be committed and complete. All right? All your locks, if you take one, are held until you do a commit. So the page and row level locks are held until commit time. All right? The key thing here is that DB2 locks anything it touches, including non-qualifying rows. All right? So say DB2 is having to read a 1,000,000 row table, and you're only fetching 10 rows out of that 1,000,000 row table, and for some reason DB2 has had to go through the table space and evaluate every row. Every row that touches gets a lock taken. So you end up with an awful lot of locks, and they're held until commit time. And the locks that are held include rows that are not returned to your program. The only benefit of repeatable read is you can issue the same SQL statement twice within a single unit of work and guarantee that you're going to get exactly the same results. All right. Now, how many times do you issue the same SQL statement twice within a single unit of work? All right. Okay. Now, read stability was added several releases ago now, but it's effectively the same as repeatable read. The only difference is that DB2 doesn't lock non-qualifying rows. So in this 1,000,000 row table example I was using, if you fetch 10 rows, only those 10 rows will be locked, not the other 999,000. Okay. All right. So other people, because those rows are not locked, you can insert rows into the table. So somebody's reading this table, and somebody else can insert rows into the table. So if they reissue the select statement later in their application, there may be some extra rows that weren't there before. All right. Okay. So if you use read stability, rereading the cursor, you'll get at least the same data, but maybe more, because other people might have inserted some rows into the table while you were reading it. Okay, question? If you use repeatable read, all the non-qualifying rows are locked as well. So if you issued the same statement, now DB2 won't allow you to insert rows into a table where there's repeatable read being used against it. Okay. Now both of these are quite destructive, and by and large you should avoid using them because they're taking an awful lot of locks for a relatively large time. All right. The most common locking isolation mode is cursor stability. And what cursor stability means is that you take a lock only when you're current of cursor. All right. It's exactly the same as repeatable read. You can only read fully committed updates, and any data you read were consistent and persistent. All right? But if you're reading through a cursor and you read a row and you don't update it and you go onto the next row of the table, the lock is released when you go onto the fetch the next row. Whereas with repeatable read or read stability, that lock is retained until commit time. So what you're doing is freeing up locks earlier, which allows more concurrent access by other users. All right. Any rows that you update, so if you've updated a row, you get an X lock, an exclusive lock. Those X locks are held until you do a commit. So I'm only talking about releasing non-X locks here. So S and U locks primarily. All right. The thing with cursor stability is even if you read the same row twice within a unit of work, it might have changed. All right. So with read stability and repeatable read, you're talking about the SQL statements. Here you're talking about an individual row. So you could read a row, not update it, think I'll come back to it later, and somebody else gets up and updates it. All right. And then finally you've got uncommitted read, UR. Now, if you look at the ISO standards, the International Standards for SQL, there is a fifth category called no commit. All right? Now, DB2 ZOS doesn't support no commit, but it actually implements it as uncommitted read. But for ISO compliance, you can actually code isolation NC in a bind statement. All right? But it's just there for compliance with standards. Effectively, we've got uncommitted read. Now, uncommitted read is a fuzzy read. You can read data even if it's locked. All right? So there's no guarantee that data you read will ever get committed. You might read data and take action on it, and then the application that's doing the update might back out. All right? The data integrity is maintained. If you're using uncommitted read applications are generally read-only. All right? But if a UR application updates a row, then DB2 uses cursor stability for the updates. All right? Now, it's important to note that uncommitted read does not mean no locking. All right? What it means is that DB2 is not going to take page and row level locks. You end up with update locks, you could XML locks, you could end up with lob locks. Right? So you do get locks, and later on I'll talk about claims, and you're definitely going to get claims with an uncommitted read application. Uncommitted read applications are generally used by things like analytics applications. But there's a surprisingly large number of applications where uncommitted read is fine. If you're reading the number of rows in a table, do you really need to know it's exactly 1 million? Or 999,199 do? Sometimes you're looking for an order of magnitude. And for those type of applications, an uncommitted read could be fine. All right. It's probably an underused feature, but you do need to be careful that you don't do it when you're doing update applications. It's generally used by data warehousing or analytics applications. Current data. Current data is a bind option that relates only to cursor stability. And everybody, including IBM, has been confused by this. All right? IBM have changed the default for this twice. Once in DB2 version 4, and then again in DB2 version 9. All right? The current default is current data no, and I highly recommend you use that. All right? Okay. Now, if you use current data, what does it do? It's read-only or ambiguous cursors. So if you have a cursor that's defined for read-only, or you do a cursor and you don't fetch a for update of clause, so you're not letting DB2 know whether you're going to update the rows or not, that's when current data takes account. And if you do current data yes, then DB2 doesn't release the rows when you're using cursor stability. So the locks are not released when you go on to the next row. All right? Now, some people have used it. I came across a site, it was in Malaysia, about 2 years ago, where they had a site standard always to use current data yes. All right? Now, the problem with current data yes is it depends on data access. If your SQL statement uses a work file, so typically you've got a sort by or an order by clause or something in your SQL, DB2 is reading the data and accessing it via a work file. Current data yes has no impact whatsoever. So if you're relying on current data yes to hold the locks, you're relying on the access path the optimizer uses to guarantee your locking. It's really, really bad working practice. Don't use it. Right. And if you look at John Campbell's presentations back in the DB2 9 time frame, he's got horror story slides. He's got some more detailed slides on this that got horror stories about it. So don't use current data no. If you're going to update a row, tell DB2 that you're going to update it. When you do fetch it, say fetch for update of, and DB2 will take a U-lock, and you're much more guaranteed to have good performance. Or you can use optimistic locking, and we'll talk about that later. So I said that you could override isolation at the statement level. There's two ways to do that. You can code an isolation clause in a DML, or in DML, you can say skipped lock data. So you can say select from skip lock data, and DB2 is going to treat that row, it's going to treat it as almost uncommitted read. Now these are advanced methods. I don't recommend you use them unless you really know what you're doing. And the other one that was added was use currently committed, which was added in DB2.10. Now that only supports inserts and deletes. It doesn't support updates. But what DB2 does is if it comes across a row and that row has been deleted, but the program that's done the delete hasn't yet committed, you'll read it as if it was there. All right. It doesn't support updates. It's horrendously complicated. There are requirements to do with current data no. There are a couple of other ZPalms involved. You really need to know what you're doing before you use this. All right. Now it was added for a purpose. I'm sure that there's a really good use case for it, but what I'm saying is it's advanced use. Don't use it unless you really know what you're doing. So I'm going to skip the next two slides because I'm beginning to run out of time. Basically, lobs are generally not locked. DB2 locks the underlying object, and it doesn't have to lock the lobs because the underlying object is locked, and that handles integrity. There are a couple of specific instances where DB2 does take a lock. They're very, very short duration, and they're there to maintain integrity across the lob. Right? The reason is a lob could be very large. It could be 2 gigabytes. It could handle multiple pages. And DB2 needs to know that when it's reading those pages, that they're all consistent with each other. So DB2 can take very short duration locks for lobs. And it's very much the same with XML. All right? So DB2 internally takes these really short duration locks on XML to make sure that the XML is consistent and that the space isn't reused. All right? But by and large, from an application perspective, certainly from a beginner's perspective, you can treat the locks at the underlying level as being the one that guarantees integrity. So what about indexes? Well, in the same way as XML and lobs, DB2 doesn't lock indexes. It uses the locks at the base level to guarantee index integrity. All right? DB2 uses this mysterious thing called a latch, which I'll cover shortly, to guarantee the integrity of the page when it's updating an index. All right? Now, one thing to be aware of is that if you see index-only access in your application, so you do a bind with an explain and you look at the plan table and it's using index-only access, DB2 still takes locks on the underlying pages because DB2 guarantees integrity at the page level, at the page or the row level, at the underlying object level. All right? So you see index-only access and you get some lock timeout on a row or a page, and you think, well, how did I do that? Because I was taking index-only access. Well, that's why. Okay?
Even though there's a primary index, primary key,
Yeah.
will not page
No. So if you update a row, right? If you insert a row into a DB2 table, then DB2 is going to lock the underlying page or the row, and that lock that's what guarantees the integrity of the index. Okay. So the reason that DB2 doesn't have to lock indexes is because the underlying data is locked. Yeah. So latches, locks are expensive and restrictive, but DB2 needs to guarantee access to objects. And an example is back here, if it's updating an index. DB2 doesn't lock the index, but it needs to make sure that two people don't try and lock the same page of the index at the same time. And to do that, it takes a lower granularity thing called a latch. Right? They're internal. They're around a third of the cost in CPU terms of a lock. And DB2 uses them to guarantee the integrity of the internal pages, for example. All right? So if you have to update an index page, DB2 takes a latch. That latch makes sure that two applications are not updating the same index page at the same physical time. And as soon as the update happens, it releases the latch. So they're very short duration, and they're there to guarantee integrity. All right? Now, there are around 30 latch classes. Another very common one is the locking latch. So there's only one lock, there's only one the logging latch. There's only one log in a DB2 system. DB2 needs to make sure that two people are updating the log at the same time. So it takes a log latch, updates the log, and then frees it. All right. These latches have very small scope and a very short duration. They're there for microseconds on the whole. Your system staff and your application, your DBAs will be monitoring for latch contention. But by and large, from an application perspective, there's nothing you need to do about it. It's the way DB2 uses to maintain the integrity of the internal page structures. Claims and drains are slightly different. Some activities, typically utilities, but also commands and DDL, need to update objects, but they don't use traditional SQL. And so DB2 uses a method of claims and drains to handle them. And they're generally, you can't issue a drain yourself, and we'll cover what these are in a minute. Now, there's nothing in a programming manual for SQL or assembler or any other programming language where you can issue one of these explicitly, but you might end up having them. So these are what claims are. So if you imagine a tablespace with 1 million pages in it, all right, and you've got page level locking. DB2 needs to know if a utility comes in, whether there's a lock on any of these pages. And it doesn't want to have to read 1 million pages in the object. Right? So it maintains a thing called a claim count. And effectively it's how many objects are using, how many applications or programs are using that object at any one time. All right? Now there are 3 claim counts maintained for each tablespace and indexes at the partition level. So there's 2 for read, there's a cursor stability and a repeatable read one, and there's a write claim. So there are 3 claim counts maintained. And when your program comes in and starts to use an object, then the claim count is incremented by 1. So DB2 knows that somebody is using that object. And then when you do a commit, the claim count is released again. It's reduced by 1 back to 0. So by looking at these claims, DB2 knows how many people are using an object at any one time. It doesn't have to look at the lock manager. All right? It doesn't have to look at the individual locks. It can just look at the claim count and know how many people are using the objects at one time. All right? Most times, claims are released at commit time. The only exception, again, is cursor withhold. So if a utility or a piece of DDL or a command comes in and it needs to update an object, DB2 can look at the claim count, and if the claim count is 0, it knows nobody's using the object and it can go ahead.
Where does it keep this in DBM?
I'd have to look that up. It's in DBM. It's in a DBM1 somewhere, I think, but I'm not 100% sure. I'll have to check that. Okay. So your application is issuing claims without you realizing it. Right? Because these claim counts are getting incremented when your application's running. Drains are disruptive. They're very different from claims. And that's when a utility gets in and it needs exclusive access to the object. So for example, you've run a reorg and you're about to go into the switch phase. So DB2 needs exclusive access to the object at the utility time. And it issues a thing called a drain. And what a drain does is it stops anybody taking a new claim, and it waits till the claim count gets reduced to 0, and then it can get access to the object. All right? All right. Now the benefit of a drain is that a utility can release a drain. So if it takes a drain and it thinks applications are about to time out, for example, then that drain can be released. Unlike a stop command, which if you issue a stop command, the application sits and waits until the stop completes. Okay? So these things are used by utilities primarily, and they can be withdrawn. All right? So it's what causes online reorgs to sometimes have problems at switch phase. So data sharing, I am really running out of time, so I've only got 5 minutes left and about 8 slides. So I'm going to jump on with data sharing. Please look at the slides. It's an advanced topic, but effectively what we're saying is that DB2 maintains all its locks at the individual subsystem level in the IRLM. And then if more than one DB2 wants to update a data sharing group at the same time, so if 2 people are accessing the same object at the same time and at least one of them is updating, then DB2 escalates locks up to the coupling facility. And these P locks get escalated, and it's a real significant performance problem for data sharing systems if that happens. But what's important is lock avoidance, because that's something that application programmers can make a significant difference on. And lock avoidance is basically meaning I want to read a page and I know that I don't even need to take a lock to start with. Right. So DB2 maintains a number of items used by lock avoidance. There's this mysterious thing called a punk bit, which is a possibly uncommitted bit. Right? And that's in the header of each row. So in every row in your objects, there's a bit that says, is it possibly uncommitted or not? Right? Okay. Now that is set on whenever a row is updated, and it's set off by various activities, primarily reorgs. Right? So if you run a reorg, all these punk bits are going to be off. And then as you update each row, the punk bit gets set on. And then eventually, you run another reorg and all the punk bits get set off again. All right. The other thing is, in each page header, there's a thing called the plog RBA, which is the page log RBA, which is the last update that was held to that page. All right. It's either an RSN or an RBA, depending on whether you're data sharing or not. And DB2 also updates the URID, which is, the URID is the RBA, it's the start RBA, the first update in a unit of work. And DB2 basically records the URID of the oldest uncommitted unit of work in a subsystem. Now in a non-data sharing system, it's called the CLSN, or commit last sequence number. In a data sharing, it's the global commit last sequence number, which is the CLSN, it's the oldest CLSN of all the members. All right? Is everybody with me? Yeah? So at any one time, DB2 can immediately work out the oldest uncommitted unit of work on that subsystem by this GCLSN number. And this is how lock avoidance works. So whenever you read a row, DB2 looks at the plog RBA, which is the last update that was made to that page. And if that is older than the oldest committing last sequence number, then DB2 knows that that page must be incomplete, because the oldest uncommitted unit of work is later than the last update that was made to that page. So if it does, the data is guaranteed to be committed and no lock is taken. If this plog RBA is higher than this, then DB2 has to check the punk bit on the row. If the punk bit is off, then DB2 knows that row hasn't been fiddled with by anything since the last reorg. And again, it doesn't take a lock. If the punk bit is on, then DB2 doesn't know whether the row has been changed or not, and it has to take a lock in the normal way. Okay? The key thing here is this thing, because if this global commit log sequence number is high enough, then you'll get really good lock avoidance. All right? And the key thing you can do as application programmers is to commit frequently. Because when you commit, that GCLSN number is more recent. All right? Now, during his session this morning, the Spotlight session, John mentioned that in DB212, the IBM are being more granular with the GCLSN. So I think they now keep 50 GCLSNs for the 50 oldest units of recovery or something like that. But they're doing things to make this lock avoidance test work more effectively. Optimistic locking is another thing that can be done by applications. Okay? And this is an application method, so this is something you can invoke with programs. So what you do is you add a row change timestamp to a table that's automatically updated by DB2. So whenever the row is updated, that timestamp gets updated automatically. All right? Then, when you read on your program, you do a read select for read only. That avoids taking any ulocks because it's taking a shell lock because you're doing for read only. And you save this timestamp in your program somewhere. And then later on, if you try and update the row, rather than doing an update where current of cursor, you do a searched update with the where clause and also check this timestamp. And you make sure the timestamp is the same as the timestamp was when you read the row to start with. All right. Now you have to put some code in your programs so that if the row has been updated since the last time you read it, something happens. But if you do this, then you're not holding locks on the object for longer than necessary, and it's a great way of doing lock avoidance. But it does require coding. All right. All right. And you do need to be careful, because if you start doing these and you do a searched update and you don't check the timestamp, then somebody could do an update and you could unupdate their update. You could back their update out. All right. So it does require good coding practice. And everybody needs to follow it. It's not something that one person can do. All right. So you do need to be careful here. But it is a good way of avoiding locking problems. So just a couple more slides. How to avoid locking problems. The first thing is start with page level locks by default. DB2 generally does that anyway. All right. Only move to row level locks if you really need them. If you do row level locking, DB2 is going to take more locks on a page, and you're more likely to get lock escalation, and you're going to have to commit more frequently. All right. The second thing is specify the intent of your cursors. If you're reading a row and you have no intention of updating it, tell DB2 it's for read only. All right? Because DB2 can make better decisions if it knows what you're going to do. And it doesn't have to guess. The next thing is commit frequently, especially in a data sharing system. Improves lock avoidance, it releases locks, it improves concurrency. There's lots of good things about committing frequently. Access your tables and rows in the same order to reduce the chances of deadlocks. Check whether you can use uncommitted read or not. Right. Avoid lock escalation, which comes back to committing frequently. Right. I'm a DBA at heart. I think any application programmer that calls lock escalation should buy the DBA a beer. Group updates till just before you commit. I see so many people updating 20 rows in a unit of work, and they update one row and then they do a whole bunch of other work and then update another row and a whole bunch of other work and update another row. Yeah. Do all your updates right at the end. That way you're holding the locks for as short a period as possible. Consider using optimistic locking, which we just covered. Co-retry logic. If you get a lock timeout, if you get a -911 or a -913 lock timeout issue, code retry logic. You see an awful lot of programs out there without retry logic in them. And then you get an application failure caused by a 911 or a 913, and your end user gets inconvenienced. They have to resubmit the transaction. There's a mysterious feature in DB2 called random indexes, which are unsorted indexes. Now they can reduce lock contention, all right? But they're at a high cost. You end up with more lock requests, more get pages, more I/O, and they're really only to be used for memory resident indexes. So if you've got memory resident indexes which are buffer pool resident, then you could consider random indexes. But they're for a specific purpose. And the last one is to commit frequently. And I know it was on the previous page, but it's the most important. All right? The more you commit, the more concurrency you get, the less locking problems you're going to get, by and large. All right? So this is my bibliography. I won't go through it because I'm running out of time. But there's some really good stuff in here. There are some old IBM documents and manuals and IDUG presentations in this list. If you can't find them, send me an email. I don't throw anything away. I've got IDUG presentations going back to the year diddly squat. I've got DB2 manuals on my laptop going back to 2.3. All right? So if you can't find anything, please do send me an email and I'll be happy to send them to you. And my email address is very straightforward. So thank you very much for listening. Enjoy the expo. Thank you.